In this video, let us learn to calculate the moment of inertia of the disk of the torsional pendulum with masses and also to calculate the rigidity modulus of the material of the suspension wire of the torsional pendulum with masses. So this table is the experimental observation. In the first column we have length of the pendulum and the next column represents time taken for 10 oscillations in 3 different positions. The first without keeping any masses on the disc, and second column represents the position 1, that is when the two identical masses are kept very closer to each other, and the third column represents the time taken for 10 oscillation in position 2, that is when the two identical masses are kept very far away from or at the extreme ends of the disc. Okay, see, for the length of the pendulum 40, the time taken is recorded in minutes. For without masses, the time taken is 2 minutes 41 seconds. And for the position 1, that is at the closer to the masses kept closer together, the time taken is 2 minutes 54 seconds. And for the position 2, it is 3 minutes 11 seconds. We could see as the position changes, the time period also changes. And see, and then for the length 50, for without masses, the time taken is 3 minutes 6 seconds. And for the position 1, it is 3 minutes 13 seconds, and position 2, it is 3 minutes 32 seconds. So, as the length of the pendulum increases, the time taken for all the positions also increases. So, it is the time taken is increasing in the row wise as well as in the as the length increases. So, why I am insisting on this is a check if in case we get a lesser time for the position 1 than without masses, that means we are going wrong while taking readings. Okay, so the next step is to convert all the minutes into seconds. See, for the length of the 40 centimeters, for without masses, the time taken is 2 minutes 41 seconds. So we have to convert all the time taken into seconds. So 2 minutes 2 into 60, it is 120 plus 41 seconds, so it is 161. And for position 1, for 40 length, 2 minutes 54 seconds, so 2 into 60, 120, 120 plus 54, it is 174. For position 2, it is 191. So this is the first step we have to do, convert all the minutes and seconds into seconds. See, for the length of the pendulum 70, for without masses, it is 3 minutes 44 seconds. So convert it into seconds. 3 minutes, it is 3 into 60, 240. Sorry, 3 into 60, 180. 180 plus 44, it is 222. For the position 1, it is 231, and position 2, 253. For simplicity, I have framed another tabular column where we are going to find L by T2 square minus T1 square. Okay, so next we need to find out the time period. So the time period is nothing but the time taken for one oscillation. Here the time taken, the oscillations are 10 oscillations. So the time period, to get the time period, we have to divide it by 10. If we have found time taken for 20 oscillation, then we have to divide it by 20. Okay, so without masses, the time period is noted as T0, and for at position 1, that is the two identical masses closer to each other, the time period is T1, and for the masses at the extreme ends, the time period is noted as T2. For 40 length, without masses, it is 161. So we have to divide it by 10. You will get 16.1. In the same way, it is 17.4 for T1 and 19.1 for T2. See, for 70 length, it is T0 is 22.2, T1 is 23.1 and T2 is 25.3. Next, what we have to do is, we have to square all T0, T1 and T2. So, square of 16.1 is 259.21 and square of 17.42 is 302.76 and square of 19.1 is 364.81 for 40 length. Then we need to find out T2 square minus T1 square. So when you do 364.81 minus 302.76, we get 62.05. So in the same way, find out T2 square minus T1 square. Then in our formula, we need T0 square divided by T2 square minus T1 square. So we have T0 here, T0 square, that is 259.21 divided by 62.05, we get 4.177. Then for 50 length, it is 345.96 divided by 76.95, we got 4.495. So finding T0 square by T2 square minus T1 square for all the 4 lengths, we get 4 values in 4.177, 4.495, 4.170, 4.628. Then take the mean for this, add these 4 numbers and divide it by 4, we get 4.3675. And the last column is L divided by T2 square minus T1 square. So we have the value for T2 square minus T1 square. For the first row, L is 40 centimeters, that is 40 into 10 power minus 2 divided by 62.05. When you do, you get 0.6446. And for the second length, that is for 50, when you do 50 divided by 76.95, you get 0.6497. And for the third reading, it is 60 divided by 95.92, you get 0.6255. See, in the last column, you could see all the readings are very consistent. That is, you got all 4 readings in 0.6. So we can take average of this 4 readings, that is, add all these 4 readings and divide it by 4, you will get 0.6443 into 10 power minus 2 meter per second square. So next next table represents the radius of the wire, which is taken using screw gauge. So using the screw gauge table, we have found the diameter of the wire to be 0.448 into 10 power minus 3 meters. So dividing the diameter by 2, we get the radius of the wire A as 0.224 into 10 power minus 3 meters. So these are the readings noted while during the experiment, that is the distance between the axis of the disc, that is the center of the torsion pendulum, and the center of the masses when the masses are at minimum distance, or that is when they are closer to each other. That is taken as the position for 1. So D1 is 1.8 centimeters or 1.8 into 10 power minus 2 meters. Then D2, that is the distance between the axis of the disc and the maximum distance from the center of the torsional pendulum, that is taken as D2. It accounts around 7.5 centimeters, that is 7.5 into 10 power minus 2 meter. And the mass of the identical masses used here is 100 grams. So it is 100 into 10 power minus 3 kilograms. In different labs, they use different masses, 200, 211, 212. So it varies from lab to lab. So here what we have used is 100 grams weight. So it is 100 into 10 power minus 3 kilogram. Then in formula, we need D2 square minus D1 square. First, let us calculate this D2 square minus D1 square. So D2 we have 7.5 into 10 power minus 2 the whole square minus D1 1.8 into 10 power minus 2 the whole square. So 10 power minus 2 the whole square will give us 10 power minus 4. That is, sorry, I have missed a power here. 7.5 the whole square into 10 power minus 4 minus 1.8 square into 10 power minus 4. So 10 point minus 4, the power is common, so we can take it outside. So on squaring these two numbers will give us 56.25 minus 3.24. in common we have 10 power minus 4. Subtracting these two numbers will give us d2 square minus d1 square is equal to 53.01 into 10 power minus 4 meters. Okay, now let's calculate the moment of inertia of the torsional pendulum disc, and the formula goes like this: I is equal to T naught square divided by T2 square minus T1 square into 2m into D2 square minus D1 square kilogram meter square. So in the second table itself we have computed the value of T naught square by T2 square minus T1 square, and the mean value of that accounted to 4.3675 into 2, the 100 grams, the mass of the identical masses, 2 into 100 into 10 power minus 3, and we have also the value for d2 square minus d1 square as 53.01 into 10 power minus 4. In the next step, let us write all the numbers together and the powers together. So the powers are written at the end. So it is 4.3675 into 2 into 100 into 53.01 into 10 power minus 3 into 10 power minus 4. So this 10 power minus 3 and 10 power minus 4 will add up to 10 power minus 7, and multiply all the numbers. You will get 46,304.2375 into 10 power minus 7, and I am pushing the powers. So when I bring in the powers, I will get 4.630 into 10 power minus 3. I am bringing a 10 power minus 4. So I'll get I equal to 4.6304 into 10 power minus 3 kilogram meter square. So this is the moment of inertia of the torsional pendulum disc with masses. Next, let us calculate the rigidity modulus of the material of the suspension wire of the torsional pendulum. So from the table we got L by T2 square minus T1 square as 0.6443 into 10 power minus 2 meter per second square, and the A value is 0.224 into 10 power minus 3 meters. In formula we have A power 4. Let us find out A power 4 in the beginning itself. So when you do A power 4, that is 0.224 to the power of 4, you will get 2.5176 into 10 power minus 3. In most of the time the students will miss to note down the 10 power minus 3 from the calculator. So be sure to take this value. And powering this 10 to the power of minus 3, 10 to the power of minus 3, the whole power 4 will give us 10 power minus 12. So totally the A power 4 will be equal to 2.5176 into 10 power minus 15 meter. The formula for this is eta equal to 16 pi ml divided by A power 4 into d2 square minus d1 square divided by t2 square minus t1 square Newton per meter square. So we know the value for, now let us substitute all the values. 16 into pi value is 3.14, m is 100 into 10 power minus 3. The divided by A power 4 is 2.5176 into 10 power minus 15, and we have the value for L by T2 square minus T1 square, that is 0.6443 into 10 power minus 2, and D2 square minus D1 square we have already computed, it is 53.01 into 10 power minus 4. So in the next step, let us separate all the numbers together and the powers together. When we separate, we get 16 into 3.14 into 100 into 0.6443 into 53.01 into 10 power minus 3 into 10 power minus 2 into 10 power minus 4. In the denominator, we will have 2.5176 into 10 power minus 15. So, next let us add all the powers and multiply all the numbers. When we multiply all the numbers, we get 171591.41. Then we add up all the powers, 10 power minus 3 minus 2 minus 4, and the 10 power minus 15, when it goes to the numerator it becomes plus 15, so it is plus 15, the whole divided by 2.5176. So when you divide the numerator by denominator, you will get 68156, and then when you add up the powers, you will get 10 power minus 9 plus 15. So then you will get from the 10 power minus 9 plus 15, you will get 10 power 6. Then taking the bringing the decimal points in front, I have moved 4 decimal points, so I got 10 power 4 here, and the numbers are 6.8156. So we have got the power of 10 power 10 for rigidity modulus. Generally we express rigidity modulus, Young's modulus, all in the powers of 10 power 10. So and many times students find it difficult only to get this power. So I hope this will help you get this, do the calculation and get the power. So we got 6.8156 into 10 power 10 Newton per meter square. So we have found the rigidity modulus of the material of the suspension wire of the torsional pendulum with identical masses technique, and the